Hi there, Ms. Barber here. I'm providing for you some worked exercises of problems similar to some of the problems of your homework assignment. Example, consider an 8-bit string. Bit is short for binary digit. Thus, a bit string is a string of binary digits or simply a series of zeros and ones. With that, we get that an 8-bit string is a series of 8 zeros and ones and can be in any combination or order. Each position of a bit string is a two-value choice. That is, it's either 0 or 1. The selection is equally likely, and the value of each position is independent. This problem allows us to use Pascal's triangle, so let's consider a representation of Pascal's triangle. With an 8-bit string, we reference the 8th row of the triangle. That consists of the numbers 1, 8, 28, 56, 70, 56, 28, 8, and 1. The number of each cell of the row represents the number of ways an event can occur. The position describes the event that is occurring. So, we'll choose to start with the left-hand side representing the number of ways a 1 is selected. Then the 1 tells us that there is only one way in which all 8 digits of this bit string is 1. Let's repeat that. There is only one way to have all ones. Now consider the number 8. That is to the immediate right of the 1. The 8 is the number of ways to have 7 ones and 1 0. Continuing, the number to the right of 8 is 28. The binomial expansion, as represented by Pascal's triangle, tells us that there are 28 ways to have 6 ones and 2 zeros. Let me repeat that again. There are 28 ways to have 6 ones and 2 zeros. So, let's answer part A. How many have 6 ones? From Pascal's triangle, so we'll write from Pascal's triangle, we find out that the number is 28. Okay. We can also compute this directly as 8, choose 6. Part B, how many have more than 6 ones? To have more than 6 ones means you either have 7 or 8 ones. Again, we reference Pascal's triangle, and to have either 8 or 7 ones, it tells us there's only one way to have a total of all ones, and there are 8 ways to have exactly 7 ones. So, by Pascal's triangle, we need to attribute where we're getting the answers. By Pascal's triangle, okay, we get that there is one way to get all ones and 8 ways to get 7 ones, and so that total is 9. This can also be computed directly as a combination of 8, choose 8, so if the 8-digit places, choose all 8 to be ones, and add that to 8, choose 7 of the 8-bit string places, choose 7 of them to be 1, and this is also equal to 9. Part C, how many end with 3 numbers that are all the same? So we still have an 8-bit string, and the first 5 could be 0 or 1. So we can have 0 or 1, 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 and 0, 0, 0, or 0 or 1, 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 and 1, 1, 1. Let's note that for the first 5 digits, there's 2 to the 5 different ways in which you can have this arrangement. There is only one way to get 0, 0, 0 for the last 3 digits. or means plus. And so, again, for the first 5 digits, there's 2 to the 5 ways in which you could do the 0 or combination, but there is only one way in which you can get 1, 1, 1. So this actually becomes 2 of 2 to the 5th, because you have 1 2 to the 5th for this one and another one. This becomes 2 to the 6th using rules of exponents, and 2 to the 6th is 64. Let C be the set containing apple, banana, carrot, date, and egg. Part A. How many subsets are there? Before we proceed, let's make note that the cardinality of this set, that's the number of elements in it, is 5. Now we can use the power set rule. The power set tells us the number of subsets is, what we want is the cardinality of the power set of C. The power set is the number of subsets possible, and for each element you have 2 choices. It's either in the subset or it is not in the subset. And so for each of them there's 2 choices, and there are 5 elements, so it'll be 2 to the 5th. That's supposed to look like a 5. And so the number of subsets is 32, which is 2 to the 5th. Part B. How many subsets contain neither a carrot nor an egg? What we need to do now is reduce the set size, and so we'll go from the cardinality of the set, and then we'll subtract the cardinality of the set that contains a carrot and the egg. And so this becomes the arithmetic problem of 5 minus 2, or 3. The set that does not contain a carrot or an egg has 3 elements in it, and then we'll use the power set rule, which tells us we take each element that's still remaining, that would be an apple, a banana, and a date, and it's either in the set or it's not, so it's 2 cubed, and that number is 8. Question part C. How many subsets of cardinality 2 are possible? The question that's asking is, in how many ways can 2 be chosen from a set of 5? We are solving for in how many ways can you choose 2 from a set of 5. This is a combination. The formula we use will be 5 factorial divided by 5 minus 2 factorial times 2 factorial. Part C. How many subsets of cardinality 2 are possible? The problem here is asking, in how many ways can 2 be chosen from a set of 5? So the problem is actually 5, choose 2. Then we'll use the formula for the combination and compute that as 5 factorial divided by 5 minus 2 factorial times 2 factorial, which is 5 factorial divided by 3 factorial times 2 factorial. 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1. Let's cancel. I'll do the 3 2 1s and 2. That'll make reduce the 4 to 2, so 5 times 2, or 10 different subsets of cardinality 2 are possible. And finally, part D, list all the subsets of cardinality 2. I'll use the letters A, B, A for apple, B for banana, C for carrot, D for date, and E for egg, and systematically select 2 starting at A. So we could have a subset that consists of A and B, moving over A and C, moving over A and D, and finally A and E. Now let's move to the right and we'll begin with B. There's no reason to pick B and A because we already have A and B, so we'll go to BC, BD, BE. Let's go to C. We don't need CA because we have AC. We don't need CB because we have BC. So we can have CD and CE. Now let's move over to D. Moving to the right, we can have DE. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Consistent. We got the 10 subsets of cardinality 2. How many anagrams does the word psychology have? An anagram is a rearrangement of the letters of a word. To solve this problem, I'm going to make a list of all the letters and how many times each letter occurs. But I'll start with, first of all, the number of letters in psychology. So, the number of, and I'm going to use the word total letters in psychology, PSY, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. Now I'll make a table and list the number of times each letter occurs. So I'll start with P, and in psychology it occurs just once. The next letter is S, and in psychology, it also occurs just once. Now I'll look at Y. Psychology, it occurs twice. The next letter in the word psychology is C, and that also occurs only once. The letter after that is H, and that occurs only once. The letter O occurs after H and after L, so that occurs twice. Let's continue. The next letter is L, and in psychology, L occurs only once. And then the next letter I see is G, and G occurs only once. And there is no need for me to list Y again because it was already listed earlier. So, what does this look like? Well, for the letter choice of P, I have 10 places and only one to choose. Going down the word. Now I have to place S, and since one of the letters is already chosen, or the spaces, I've only got 9 spaces left, and there's only one S. The next letter is Y. And so we've got 8 spaces to fill and 2 Y's. Now the next part is tricky because I'm going to go to the letter C, but we already took 2 spaces for the Y, so instead of 7 spaces left, we've got 6 spaces left and 1 C. The letter after that is H. We've got 5 spaces and 1 of those. Now the next letter I'm going to look at is O. And so we got 4 spaces left, but 2 occurrences of O. After O, the letter I'm looking at is L. And again, let's be careful. 2 spaces were taken up because O occurs twice. So instead of having 3 spaces left, we actually only have 2 spaces left and 1 L. And then for G, we have 1 space left and only 1 way to choose that. Now let's expand this a little bit and see how it looks. 10 choose 1, we can write that as 10 divided by 1. 9 choose 1. Now, when we use the expansion, this will be 8 times 7 divided by 2 times 1. And then 6 choose 1. 5 choose 1. Now we've got 4 and 3 divided by 2 and 1. And then, this should just be times. 2 choose 1. 1 choose 1. Now let's expand this out a little bit. If we look at the numerator, we got 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in the denominator, ones don't really matter, but I do want to write we have a 2 times 1 and a 2 times 1. This is 10 factorial divided by 2 factorial times 2 factorial. Note, we did a factorial of the total number of letters, which was 10, and then divided by factorials of the occurrence of repeating letters. And so y occurred twice, we did 2 factorial. O occurred twice, we also did 2 factorial. To compute this number, use your calculator. So do 10 factorial in your calculator, and the digits you'll get are 3628800 divided by 2 factorial times 2 factorial is 4. And we find that there are 907,200 different anagrams of the word psychology. Most of them probably will make no sense, but that's the number of rearrangement of letters that are available. Example, a 5-digit number contains digits from the set A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Part A, find how many distinct 5-digit numbers are possible if a digit can be repeated. So we are looking at 1, 2, 3, 4, 5-digit spaces to fill, and for each place we can have 9 possible digits. 1, 2, 3, 4, 5, 6, 7, 8, or 9. And we do that for the 3rd, 4th, and 5th space, so we have 9 to the 5 possible distinct 5-digit numbers when digits are repeated. Part B, find how many distinct 5-digit numbers are possible if digits cannot be repeated. And for numbers to be distinct, order does matter, so we're looking at a permutation. We want a permutation of 9 numbers taken 5 at a time. And finally, the last one is C. Find how many different 5-digit numbers are possible if the first digit must be even and no repeated digits. So we still have 1, and then we have 1, 2, 3, 4 more places. If the first place must be even, we look at the digits and we see that there are 4 even digits, 2, 4, 6, and 8. So from the 4 even ones, we choose one of those numbers. And then for the remaining 4 places, we're going to need to select 4. One of the even numbers is gone. We still have 8 other digits from which to choose. So the result is 4 choose 1 times 8 choose 4.